artificial neuron model and linear regression. Now, in the last class, we had given you an introduction to the biological neurons, right? What we discussed there was that the human brain, okay, is able to do enormous amount of computations, okay, and in a very short time, utilizing the billions of nerve cells, okay, or the neurons, okay, which are existing in our brain. And as I explained in the last class, that these neurons are interconnected to each other, okay, in the form of a network, in fact a very complex network. I mean, it's not that we understand fully about all the different connection mechanisms of biological neural networks in a complete way, okay. Whatever we know is mostly from the experiments been performed, and this is mostly the scientists' observations and beliefs, okay, which I mean has led to some kind of a model making for the biological neurons. And essentially it is the biological neuron model which we will have to adapt, okay, in order to do the computations for our purpose. So what we are considering is the artificial neuron model, and the name artificial itself means that it is different from that of the biological neurons, okay. The first thing is that we, in a typical artificial neural network structure, we are not going to consider so many number of neurons. I mean, it's only a small manageable number of neurons that we are going to consider, okay, that too for solving specific problems. And as I told you, that if I have to list out the different applications of neural network, then that list is never going to be complete, because we can imagine the applications of neural networks in any application domain. I mean, be it science, be it technology, be it any type of market forecasts, weather forecasts, I mean many applications, okay, signal processing, biological applications, where we can, I mean, apply the neural networks in a very big way. And in fact, I mean, neural networks along with the fuzzy systems, okay, they are very popular. They are going to be very popular for the I mean domestic appliance controls, okay. I think all of you must have heard about that, the neuro fuzzy controllers. So there are large number of applications which I mean one can think of. Now, coming to the model of the artificial neuron, okay, it needs some introduction. Now, as I was discussing in the last class, that the biological neurons are interconnected to each other, okay, through what is called as the synapse, okay. So I made a mention that it is the synapse which is basically deciding about the strength of the connection, how strong or how weak those connections are. Typically, a nerve cell or a neuron could be connected to several other neurons, or it might be receiving inputs from several sources. So if we look at a neuron in isolation, supposing this is a neuron that we are going to consider, and there we are basically receiving inputs from a number of sources, right? So there are plenty, and I am just drawing a few, okay. This may be the input number 1, this may be the input number 2, input number 3, and so on. We may be having n such inputs. So I just happen to number them from 1 to n, okay. And they are connected to this neuron which is going to do the processing. Now, these neurons are connected to these ones using the synapses. Now, synapses are existing in the biological neural network, as I explained, but a very similar concept we drew up for the artificial neurons also, okay, where we model the strength of the connections this way. So, we call the strengths of the connection as the synaptic weights. So, the strengths of the connections will be known as synaptic weights. Weights, they decide that how much of strength it is. So, larger the value, more strong the connections are, okay. Smaller the values, less strong they are. In fact, I mean, there is no binding that whether the synaptic weights must be only positive or not. As a matter of fact, it could be positive as well as negative, because even for biological neurons also, or biological, the synapses associated with the biological neurons, which we discussed in the last class, we said that they could be either excitatory or could be inhibitory in nature. Now, we will be having such synaptic weights which will be associated, and those synaptic weights will be defined for the connection between the input and the neuron under consideration. Now, mind you, the input may be received from other neurons also, or the inputs may be coming directly from any of our perceptual units. Okay. So, no matter whatever the sources of the inputs are, basically we are receiving the inputs from some source, and there are a large number of neurons existing, and let us pick up a small, one particular neuron out of it, and let us say that we index this particular neuron by the letter K. So, this is a particular neuron K that is under consideration, and this is receiving a number of inputs, and these are having connections or the synaptic weights which will be written as WK1, WK2, WK3 and so on, and this one will be WKN. Okay. So, the notations that we are using is that WKG basically indicates the connection strength from the neuron J to the neuron K. I mean, if you are considering all these inputs to be neurons, okay, which in typical cases it will be like that. Okay. So, WKJ will indicate the connection weight from neuron J to neuron K. So, please note this order, it is not K to J. I mean, it is not always the case that the connection which is existing as WKJ will be equal to WJK. Okay. In fact, the feedback path may or may not be existing. So, the way we are indicating this does not mean that there is any connection between K and N back or K and 3 back. If there is a connection, okay, then we will be indicating that by a separate weight. For some applications, WKJ may be equal to WJK, but KJ always means connection from neuron J, the superscript that we are writing after, and K, the superscript that we are writing before. So, K is this neuron. Now, when these sort of strengths are defined, okay, and we can define the inputs as x1, x2, x3 and so on up to xn. Okay. Now, we are linearly combining all these things. So, in effect what it means is that we are summing up all these inputs, okay, multiplied by their appropriate weights, so that the sum total, okay, which we can call as the UK will be equal to summation of j equal to 1 to n WKJ, and this has to be multiplied by xj. So, it is summation of xj wkj, and the summation will be from j1 to j equal to 1 to n. Is this clear? So we are adding up all this n different weighted inputs, effectively linearly combining them together. Okay. Now, to this we often require to, so this will give us some kind of an activation value, okay, some kind of, weighted addition that we have made, and we may like to move this whole thing up or down, okay, just like adding some DC offsets to it, okay. Those who are familiar with the operational amplifiers, they know that whenever we are combining some inputs, okay, to the operational amplifier, using it as a summer, we can add some DC also to it, so that the whole summed input can be raised up, or if the DC is added in the negative direction, the whole thing can be brought down. So it is a offset, or what we can call as a bias, that can be applied. So we can in fact say that this bias, okay, that also will be used as an input to this system. So this bias I can call as BK. Again, the subscripts K for UK and BK means that they are pertaining to the neuron K over here. Okay. So that the combined output of this will be VK equal to UK plus BK. So it is the bias, and with that we add up all these weight multiplied by these inputs. Okay. Now the thing is that this is the VK, and we are interested in finding that what kind of a response is this neuron going to give us. Okay. That is very important, right? Basically to determine that only we have considered this artificial neuron model. All right. Now, there are several ways whereby we can define this function, and the simplest of that is to consider a threshold function. The threshold function can be defined like this, that you see that the combined output from all this is what? This one, Vk equal to Uk plus Bk, and Uk is this summation and Bk is the bias that we have added. Now we can say that this will result in the activation like this, that if Vk is equal to, supposing greater than or equal to 0, okay, then we can say that we are going to design the neural network, or design this neuron in such a way that, followed by this, if we take this output, okay, and we just pass it through some function, let's say this is a function of Vk, okay, and this will be the overall output. So we are going to define this function now as a threshold function. How? That if this Vk, that is the total response over here, is greater than or equal to 0, then the final output, okay, if we can call this as Yk, okay, the final output of this, okay, if Vk is equal to 0, is greater than or equal to 0, we define that Yk is equal to 1 and Yk is equal to 0 otherwise. Otherwise means that when Vk is less than 0. That means to say what? That Vk can assume any value in the range of, could be a positive, could be a negative value, And in this case, we haven't really put any binding on the value of Vk. Vk could mean anything. I mean, theoretically, I should say it can go from minus infinity to plus infinity, but the output is hard limited. Okay, we call this as hard limit. So the output is hard limited to 1 or 0. Okay. So if you plot the response of this threshold function, that would look something like this, that on this axis we plot Vk and on this axis we plot Yk. So this necessarily means that at Vk equal to 0, we are going to see a discontinuity in the function definitely. As long as Vk is less than 0, okay, we are going to have the value of Yk to be equal to 0. So this is Yk equal to 0, and this is the point where we are going to make the Yk equal to 1, okay, and this is the positive direction of Vk. So this is towards plus infinity, and this direction is towards minus infinity. So as long as it is less than 0, Yk is equal to 0, and when Vk is greater than or equal to 0, with a discontinuity happening at Vk equal to 0, the Yk is going to be equal to 1. So this is a threshold function that one can use, in which case the response of this neuron, okay, is going to be absolutely binary in nature, right? Now, in this case, we considered that the outputs are going to be 0 or 1, right? But there are some applications where we do not require the binary values modeled as 0 and 1. We quite often need applications where the output is to be modeled as -1 or +1. Okay. And if it is -1 or +1, in that case, we have to define this function f to be a signum function. Okay. In that case, we are going to define the threshold function like a signum function, signum of Vk, meaning what? That if Vk is greater than or equal to 0, then Yk is going to be equal to +1. So Yk will be signum of Vk, meaning that Vk greater than or equal to 0, Yk is equal to +1, and with Vk less than 0, Yk is going to be -1, right? So here the function would look very similar. Okay, it will be -1 up to here, then a discontinuity at Vk equal to 0. Okay, so this axis is Vk as before, this is Yk, and beyond Vk greater than 0, we are going to have Yk equal to 1. So this is the value of 1, this is the value of -1, almost the same thing as that of the threshold function. So this is also a hard limiting only, restricting the value to 0 and 1 or -1 and +1. In fact, this particular neuron model, okay, where the response Yk can be either 1 or 0, and it is defined as a threshold function like this, these neural models are known as McCulloch and Pitts neural network model. So this was originally proposed by them, McCulloch and Pitts. So this is often known as the McCulloch and Pitts neural network models. Okay. Now, it is not always mandatory that the neurons will behave in this manner only, because after all, the kind of problems that we are going to solve with the neural networks, okay, there a wide range of variations in their response is quite often needed. So if we are living with the analog world, like say for example here, we did not put any restriction on the values of this x1 to xn's. They are analog, they can vary in any manner you like, and the Vk, on the Vk, on the sum, there also we did not put any restriction, right? But we are only restricting the output, but why do we restrict it always? We need not have to do that. So what we can do is that we can propose a different model also. Now for a very simplistic model, why don't we consider the linear model itself? By linear model I mean to say that what is the problem if we do not choose any f function out here and we take this output directly? That means to say that we make yk equal to vk. Okay? If we make that way, then our model gets quite simplified. In that case, how will be the input output characteristics? Pretty simple, because if we take a linear model, in that case we can plot it like this. This axis vk and this axis yk. So when vk is equal to 0, we will have yk equal to 0, and when vk is something, let's say a value equal to a, yk also will be having a value equal to a, because we are going to have yk equal to vk only, so that it will be a perfect straight line, okay, with a slope of 45 degree and passing through the origin. It will be a perfect straight line. So that will be our perfect linear model for that. Okay. In fact, just to represent the neural network in the form of a linear model, okay, we make some simplification in its structure. You see, so far we are taking the bias and the inputs separately. Okay. In fact, it is possible to include this bias, okay, as a part of the inputs only. Means that we can model it like this, that you see here we have got the numbers ranging from x1 to xn, they are the inputs. So we can have an input which we can call as x0, okay. So x0, and that will be connected to the neuron, and then we can have the other inputs as it is, that's to say x1, x2, x3 and so on up to xn. This is xn, all right, and this weight we are going to call it as wk0, okay, so that we have x0 wk0 to be equal to bk. Okay. So what we are simply doing is that this bk, rather than representing as a separate bias connection, we are representing it in the form of an input only. After all, bias is also an input, but we are just modeling this way. So wk1 so this is wk0, this is wk1, this is wk2 and this is wkn, so that what happens is that when I write the expression for vk, I can simply add it up like this, xj wkj, and in this case I sum it up from j is equal to 0 to n. Okay. So that is the only difference. Earlier I was calling j equal to 1 to n and then adding the bias to it in order to realize vk, and in this case I am simply describing it by a single equation, that summation xj ykj. Okay. Now in this case, actually in a linear model, okay, if it is a perfect linear model, then we are not making any restriction about the values which vk and yk can assume, because like before we are taking the value of vk in the range of -infinity to +infinity. Okay. So Likewise, yk also can be in the range of minus infinity to plus infinity, but quite often for practical consideration we tend to put some hard limiting threshold, okay, beyond some range. So, if it is such that, I mean, from a practical realization point of view, that this is the point beyond which our hardware cannot process the signal, okay, we can put a hard limiter out there, okay, so that between some range, I mean between this range, we can use it as a linear model. Okay. So, when we talk about a linear model, that necessarily means that within our expected range of operation, okay, it is going to follow a linear response. It is going to follow this equation which I have just now mentioned, that is to say summation of Vk is equal to summation of xj wkj and summation ranging from j is equal to 0 to n. Okay. Now, this is a linear model, and let us try to see that what could be the application of that. Okay. Where are we going to use this kind of a linear model? Basically, we can use it for any data fitting where we have to fit a straight line to a given set of data. Maybe that we have conducted some experiment, okay, and the experimental data is showing a large number of variations. Let us say that this is the input, okay. We have noted some input output characteristics, so that we have set some inputs, and for those inputs, okay, there will be some output values. Maybe that when the input is this much, we have got output this. Maybe when the input is this, the output is this. Maybe for input this. So, like that, there could be a set of points that we can obtain. Okay. So, this may be the data that you have collected from any experiment. Can be a scientific experiment, can be any experiment that you would like to do. Let us say, let us take some very simple example. Supposing you are trying to plot the weight of a person against the height. Okay, so on this axis we have weight, and on this axis we plot height. Now, it is known that generally the persons having, I mean the persons who are taller, they tend to have more weight as compared to the persons who are short. Okay. Not always the case, because I mean the weight of a person is not dependent upon height alone. The weight in fact will be dependent upon so many factors. I mean his height, his basic physique, okay, then his I mean food habits, okay, his calorie intake, fat intake, I mean his dietary habits, then also how much of calories he burns, okay, how much of exercise he performs every day. On so many factors the weight of a person will be dependent. But we are only studying that how is the weight changing with height. Okay. So, maybe that we conduct an experiment on 1000 people, okay, and we make a plot like that, I mean against height we plot the weight, and this may be a set of data that we obtain, right. Now, our objective may be to fit a curve, okay, fit a curve that passes best through these set of points. We do such kind of curve fittings in experiments, isn't it? Now, whenever we are applying a linear model, we would necessarily fit in a straight line to this set of observations that we have made. Okay. Now, whenever we want to fit a straight line, then we have got two free choices for that straight line. What are the free choices? The intercept and the slope, right. A straight line will be characterized by the intercept and the slope. I mean, if we are writing in the popular form of y is equal to mx plus c, m being the gradient, okay, or the slope, and c being the intercept, okay, then that's the way whereby we can model a straight line. And in fact, we got a free choice that we can vary m, we can vary c, okay, in any manner we like. I mean, that means to say that if we do not have any a priori guesswork available, okay, what we are going to do is to fit a try out with wide varieties of m and c, and finally coming up with the best type of straight line fitting. Okay. We know that the best fit straight line would be somewhere over here. Okay. But somebody may like to fit the straight line like this, somebody may like to fit the straight line like this, in which cases we know that it's not an appropriate straight line fitting. Now, supposing that we have fitted a straight line, we have managed to fit a straight line like this, the best set of m and c we have chosen. Okay. From this set of experimental data. Now, there are some points, okay, which are lying above the curve, there are some points which are lying below the curve. So, like that, I mean, there are a large number of observations that we have made, okay. And if you see, I mean, if you take any particular point, like say for example, I take this height, okay. For this height, I have got this to be the difference or the error between the actual value is this, and the fitted value is this. So, this is an error, okay. Whereas for this one, the error is here, okay. So, if I take this to be a positive error, this one is a negative error, okay. Now, I have ways to make the error positive, because if I take the absolute value of the error, or if I take the square of the error, okay, and if I add the square of the errors or the square of absolute errors, then I will get a combined error measure, and if I divide it by the total number of points that I have used in the experiment, I will be getting the mean square error also, which is a measure that how good or how bad my curve fitting is. So, in this case also, it is going to be a straight line fit that we are trying to do, okay. And very interestingly, the equation that we are going to write for this is of the form of y is equal to mx plus c only. Only thing is that instead of writing it as y is equal to mx plus c, according to our notation, we will write it as y, call it yk, okay, because again, if we are processing these using the kth neuron, call it as yk, okay. Yk will be equal to, okay, w1x plus w0. If I write it in this form, what does that mean? Then w0 indicates the intercept and w1 indicates the slope, all right. What is x? X is the input, x is the input to the system. What is the input? The height, okay. We are seeing the person's height, and against that we are plotting the weight, okay. So, x is the input to it, and w1 can be defined as the synaptic weight between the input and the output. Okay. Now, in this case, that means to say that we will be having only two neurons, right. So, it is the neuron 1, okay, and it is the neuron 2. Let us not call it as k anymore. We have neuron 1 and neuron 2, and neuron 1 is connected to neuron 2 by the synaptic weight, which we are now going to call it as W21 or 12? 21, because it is WKJ as we had said. So, we are going to write it as W21, and this, it is the neuron 2 which is doing the processing, and here we are going to have an input equal to plus 1, and this will be multiplied by W0, not exactly W0, this is W20, okay. so that the overall response, that is y2, will be equal to W21 into, here the input will be, I mean although I have written it as 1, 1 is the neuron number, but its input will be x. So, it will be W21 into x plus W20. So that the whole thing is modeled as a very simple neural network, okay, whose response will be, in this case, y2. It is a linear response that is being made, okay, and the input to this is x, okay, multiplied by W21, the synaptic weight, and W20, this indicates the bias. So, the bias in this case indicates the intercept. So, the bias stands for the intercept, and W21, that is the synaptic weight, that stands for the slope. So, this is the slope and this is the intercept. So, we can, so that means to say that fitting a straight line to this set of data means that modeling it to a neural network, because after all what we have to determine, just like the way to fit a straight line, we have to make a good choice of this M and C. Very similarly, we need to have a good choice of this W21 and W20. If we can make a good choice of W21 and W20, then the job is done. And what job is done? Like in this case, you see that if somebody gives me the height of some unknown person, means this is the set of data that I have gathered during my experiment, during my trials, I have gathered this data. So, now that I have got this data and I have fitted a straight line, if someone else's data is put in, or if I know the height of somebody, okay, then I can easily use this curve in order to say that if it is given that, okay, the height is this much, then the corresponding weight will be this much. That is what we are going to say, because this will be the weight that we are going to interpolate out of it. Okay. So, likewise here also what happens is that once the neural network is trained, okay, with some patterns, with some inputs, okay, and you feed some unknown input to this system, okay, in that case it will be behaving with whatever weights with which it has already trained. So, the neural network has already trained itself with some W21 and W20. That means to say that it has already fitted a straight line like this. So, now if we just feed some unknown input to it, then we will get the corresponding output, which will be as per the fitted data. Correct?
This will be in some probability, like you have fitted a straight line.
That's right.
Chances of the person having that height, having a weight, there will be some chances, not exactly.
Well, I mean, let's not talk in terms of probability at this point. All that we are trying to say is that, okay, this is the fitted data. So, I mean, because it is an unknown data to it, I mean, we can at best conclude that we are going to have this particular point. Now, I mean, how good or how bad that is with respect to the actual data, that we are not knowing yet. Okay. So, it is after conducting a large number of experiments. In fact, to be very honest with you, this experiment is not at all a good experiment, because as I was telling you that here I have assumed that the weight of a person is dependent on only one factor, that is the height, which is not at all true. It is dependent on many factors. So, in fact, if we now start listing the different factors to which it is related to, in that case we are going to get different curves. Like if now, for say for example, I plot a curve as weight as plotted against the average calorie intake of a person, okay, then also I will get a separate curve out of that, okay. Or I mean, all the parameters with which something is dependent upon, okay, if I plot all these together, then effectively I will not be getting a model like this, but for each one of the inputs, okay, I am going to get a straight line fit of this sort of nature, so that ultimately it will be a combined fitting of linear response. Okay. In fact, I mean, yeah, it will be like this, that supposing there is some output, okay, let us say that the output to this neuron is dependent upon this two set of datas. Okay. So, I say that these are coming from the neuron 1 and the neuron 2, and supposing this is the neuron 3 whose response we are trying to find out, and also there is a bias, so that I say that this is plus 1. So, this is W30, this is W31, this is W32, and then this one will be the Y3. In this case, what happens is that your Y3 will be equal to W30, that is to say the bias, okay, plus W31, we call it as X1, plus W32, we call this as X2. Okay. So, this will be the combined output, okay, so that we get. So, now that Y3 is dependent upon two inputs, Y3 is a function of X1 as well as X2. So, we get two slopes pertaining to that, one associated with X1 and the other that is associated with X2. So, this is a two dimensional problem now, or rather modeled it as a two input network, and like this we can extend. So, essentially it is a data fitting problem that we are doing. And let me also tell you about, I mean, it is not that always it will be linear curve fitting that we are going to do. Supposing the observed data is, say, of this pattern. Supposing this is the input and this is the output, and the observed data pattern is like this. Supposing this is the observed data pattern. Now, somebody tells me to fit a straight line on that. Okay. We can do this straight line fitting, but the straight line fitting will not be certainly an appropriate fitting. I mean, if I try to feed the straight line like this, okay, you can see that that particular straight line, how best you can think of, okay, will be having lots of deviations from the actual point. Okay. So, in that case, we have to consider, or we have to go in for some non-linear model. Okay. So, do not think that the linear model is able to solve everything, okay. But okay, for the time being we restrict ourselves to linear modeling, at least in this lecture. So, now let us think that what is going to be, I mean, because of this straight line fitting, we are certainly going to make some error, isn't it? There are number of points which are in error. So, how do we represent those error? Let us say that the error is represented as E, okay, and error for a particular point, let us say EP, I write EP will be equal to the target output for the point P. Like say for example, again in this curve, supposing I am interested in finding out the error that is happening at this point. Okay. Now, supposing this is point P is equal to 1, the first point I consider. Okay. Now, this one is having this as the actual output, or what we can call as the target output. So, this is our T1, the target output, and this is the response that we have got after curve fitting. And after curve fitting means what? That is what the neural network is giving us, because neural network is doing that curve fitting job essentially, isn't it? So this is the response, okay, or rather in our case it will be yk, okay, or the output. So if I say that the response for the point P is yp. Now, okay, let us not use the subscripts, let us use the superscripts, because the subscripts we were using for the neural network index. So I think it will be creating unnecessary confusion if I use the subscripts there. So instead let me represent it as superscript. So I say EP as the error pertaining to the point P. So which will be now defined as the target output for the point P minus the actual observation, I mean the actual output, which will be the fitted output. The fitted output will be here, this one. So this will be our yp. So this will be yp, which will be the fitted output or the neural network response, okay. And if I square it up, in that case I will be getting the error term, or rather the squared error, okay. And what I have to do is that in order to determine the total error for all this set of points that I have got, I have to define as summation of this EP and to be summed up over P, okay. Means whatever points are there under this set of P, I have to include all of them, which means to say that it will be summation of this TP minus YP whole square, okay. This will be the summation of errors, all right. Now, why do we measure this error? Okay, because this error measurement is very much necessary, because if we start with any arbitrary intercept and slope for this straight line, okay, we should measure that error, and then we will find out that in what direction we should adjust the slope and the intercept, so that next time the fitting that I do can be a better fit. So if I start with some initial assumption about the intercept and the slope, okay, or to talk in terms of the neural network, if I start with some initial assumption of this W1 and W2, okay, then what I have to do is first measure that how much of error am I doing in the process, and then dependent upon that error, okay, I have to adjust these W's, or in terms of this I can say I have to reorient the straight lines, intercept and the slope, so that next time the fitting is better. Next time also I do the same measurement, that with the better fitment I calculate the errors, okay, the error over all the points P, okay, and I this time come up with a new error measure. This new error measure may be less or better than the earlier error that we had got. Accordingly, we reorient the straight line. Say for example, supposing this is the initial, I mean this is the final straight line that we have fitted, okay, but supposing with the initial set of points I place my guess to be like this, that this is the initial slope. Now I slowly turn this so that after a few iterations I get the straight line fitted as follows, okay, where the error becomes minimum. Because what happens is that if I try to orient this straight line more, then again the error will be increasing, isn't it? So we are orienting from here to there, and then we are finding out that where the error becomes minimum, okay. So our objective in a neural network also to be to find out that where are we going to find that minimum error. If we now start making a plot of, let us say in this case, in this simple kind of neural network that we have considered out here, okay, take this model, all right. what we are doing, we have got x as the input and we have y as the output, right? And we are going to adjust which parameters, W20 and W21, in order to determine the minimum error. So what we can do is that over all these set of points, okay, we can calculate that how much of error, I mean how much of combined error measure, that is E, we obtain for different values of W21 and W20. And supposing we make a 3D plot like this, 3D plot where let us say that on this axis I put say W20, on this axis supposing I plot W21, okay, and on this axis I plot the error, okay. So it is a 3D plot now. Can you imagine? It is becoming a 3D plot. You vary W20 in its entire range, you vary W21 in its all possible range, and there is one particular solution where this straight line is going to have the best fit, and there the best fit means that where the error is going to be minimum. So it will be ultimately a surface like this, okay. It is a 3D surface, okay, that can be imagined to be like this. I mean, if this is a surface, then I mean you can, okay, you can imagine that this is a 3D surface which will result out of all the possible values of W20s and W21, and there will be one particular point where we are going to get the minimum E, and that is the point which we want to reach. Is it followed? That is the point where we want to go. Now, okay, imagining a 3D surface is little difficult. I mean, we find it difficulty in visualizing a 3D surface. So let us visualize in a better way. Let us put a cutting plane and just try to observe the 2D projection of that, okay, on that particular plane, okay. In that case, our problem in a 2D could be modeled as follows, like if we have a curve of E, okay, supposing on this axis we are plotting E, and let us say that instead of two variables here, W20 and W21, we have got only a single variable, okay, some variable which we have plotted in this direction. Now we are going to reach the minimum point over here. But what could be our starting point? To start with, in this example, in this case for example, we could start with any value of W20 and W21, okay. We could be on this part of the surface, we could be on this part of the surface, we could be anywhere on the surface, okay. But ultimately we would like to reach this as our destination. If we could reach this destination, then I can say that the problem that I am going to solve with this kind of a neural network model is going to converge. If it doesn't, then really I have to doubt about the usage of this kind of neural network models at all, okay. It has to reach this. So what happens is that if this is our starting point, I mean on a 2D error profile, if this is the starting point, okay, then just see what happens is that if you are considering this error curve, this error characteristic, error versus some parameter, supposing this is a parameter W that we take, okay, then if you are taking the partial derivative of this E with W, okay, assuming that a very similar plot you also get for the other W's also. So E is not dependent on this W alone. So that's why it is a partial derivative that we decided to take. Now in this case, what happens is that what is the slope of these dou E, dou W, okay? The slope is like this, okay? It is in this direction, but if we are in this position, then on this curve, with respect to this curve, we should slide down in this direction, isn't it? We should make a slide down in this direction, so that by sliding down further, we ultimately come to this point. Okay. We may not be able to reach this point, this minimum point, in one iteration. We may take several iterations in order to reach it, but ultimately we should reach it. Okay. Something you can imagine like this, that you get a bowl, okay, where you have just placed some small ball over here, okay, and you have allowed that ball to roll down the surface of that bowl. Where that ball will ultimately reach? The ball ultimately comes to the point of minima, isn't it? Okay. If we allow the ball to slide down freely, okay, if we do not allow it to slide down freely, if we try to forcibly make it, okay, things may be good, things may be bad. Okay. Like if the surface is having lot of friction, let us say, in that case the sliding process will be very slow. It will very slowly slide down, so we may feel impatient about it, and we may just put some taps so that the ball slides down faster. But if we are, too much ambitious about its fall, that no, the fall should be much faster than that, then we are going to shake it so vigorously that it may ultimately leave the surface completely and just the ball will fly away. Okay, it can happen. So we have to be careful about that, but the objective is that if you allow it to roll down freely, then it roll down, okay, in the gradient descent, in a gradient descent way. If the ball lies here, it comes down this. If the ball lies in the opposite slope, that means to say here the slope is this is in this direction, but the ball has to roll down like this. So it is always against the slope that it is sliding down. So this technique is known as the steepest descent. Okay, steepest descent approach. So this will be something that we will discuss further, okay, in the next class. Okay, any